Hello, and welcome to tutorial number 24 of this year of 2020, where we're going to take another look at differential growth script that we've already done in our tutorial number 22, I believe. The difference between that previous tutorial and this one is that we're going to be looking into how to use differential growth, or rather how to grow a curve on top of a three-dimensional surface rather than a two-dimensional plane. And hopefully it's going to give us a nicer result, or at least a different result from what we got from that tutorial number 2020. I will be going fast with the first part of it, at least first part of the script, because we've already done that, right? So if you want more in-depth look, then you can definitely visit the channel and go to tutorial number 22 right here, and then you'll see all of the explanations of what at least the first part of the script does. So to start things off, I want to create that growth algorithm, right? So I will be growing a curve, and let me just draw a squiggly line here like that, and I'll be using that as my reference, and I will be just referencing it into Grasshopper. So now it's here. Let me hide it, and I will be rebuilding it as a polyline. So I will divide this curve into, let's say, let's go for 500 points for now, like that, and I will just create a polyline through those points that we've got. So now it's basically just a bunch of straight line segments chained into a single polyline. All right, again, everything more in depth is in tutorial number 22, so keep that in mind. Now I'm going to explode this polyline, and also I'm going to grab its discontinuities, just to have everything linear. And why the hell do you do that? Level, I will just choose a different level. Let's see, curvature. There we go. So that seems to be fixing it. That was weird. Anyway, so I have my discontinuities, and I just exploded. So here I have my segments. So every separate line segment is here, every point on my lines are here. Okay, now we're going to go into Kangaroo and use a solver as per usual, and I will just use Entwine node. Or do I need an Entwine for this? No, I don't. Okay, I will not be using an Entwine node, sorry. I will be using a Merge node, and I'll just connect it to goal objects. Reset will need a button, and on or off toggle will need a toggle, right? Just like that. For now, I'll keep this off. All right, I will not be messing around with threshold or tolerance. Okay, so now what kind of goals do we need? Well, we need these line segments to grow, so I will use a goal that's called, I don't remember, goals under length line. This goal right here, and I'll connect my segments, and I need to give them, I need to be able to control how long I want them to be. So before I begin, I will just specify, let's say, give me all of the lengths. So with length node, give me all of the lengths of these line segments. So here as an output, I get all of the lengths, and I will get all of their averages. So an average length of all of these separate line segments that I have here. Zoom in. So all of these are separate line segments. So I get all of their averages, average lengths, and that's 0.178, whatever, doesn't matter. And I'll just create a slider between 0 and 10, something like that. Or should it be, no, it should be between 1 and 10, right? 1 and 10, and I will just multiply. Multiply the average length by 1, let's say, and connect it to the length input here. So what this does is when the slider is at 1 here, it will just use the average length for all of these segments, so most of them will not change, right? But once I keep increasing it, it's going to start expanding those every line segment to that particular, multiplied length. Okay, so length line goes into D1, like that. And actually, I believe I can start showing what kind of output we get if I just disable preview of everything, also disable preview of the solver. Here as a V output, we get all of the points that are in play. So I can rebuild a polyline through those points that are in play during the simulation, right? All right, so we have that going on. And then let me hit reset and let me run it. And now you can see that it doesn't change. That's because we're multiplying the average length by 1. But if we start multiplying it by a larger number, you can see that the line segments grow, but they're all really messy. And that's normal, right? That is normal. Let me stop the simulation and reset. That's because they don't care if they intersect one another, right? So we need to fix that intersection. And this is where collision comes in, where we use sphere collisions, right? Sphere collisions, and I will use, actually, probably we should do this. This one goes in the top and this one goes in the bottom, like so. Just not to cross any wires. Okay, so sphere collisions works with points. That's exactly why we used discontinuities here. And I needed to use C2 rather than C1. I just right click on the L input and I can switch between these. So we use points and we create like spheres around each point, and we specify what kind of radius they will have. And those spheres will bounce off from each other, meaning that the lines as they grow will not be able to cross one another, right? So for the radius, I will say, for now, let's just use the same number as we're using for the explode here. So radius comes in like so. We connect it to D2. We should be good to go. Okay, let's reset and run it, and then start, or rather disable preview of this, and start increasing the slider. Super, and we have our growth. That was easy, right? And as you can see, it's bouncing off from one another. Okay, so now what if for the radius we specify, we divide division, we divide this number by some amount, let's say somewhere between 1 and 4. Like that, radius. And let's try and see what happens if we divide this value by 4 and then run turn off the simulation, reset, run it again. Oops, sorry, turn off, reset, pull the slider back to 1 and then run the simulation, and then as these lines are expanding, the spheres will be 4 times smaller than they were before for collision detection. So as I'm, let me go in here, as I'm increasing the value, you can see that some errors are starting to appear, right? So that means 4 doesn't work. Okay, good to know. Let's try 3 and see what happens. Reset, expand, and 3 almost works. In some cases it kind of fails, but 3 almost works and it makes this pattern. So let's try with 2. Even changing it to 2 already fixed it, but I'll just, whoops, that's way too fast. I will reset it. Come on. Reset it. Run it. And always increase the slider slowly to make sure that there are no intersections. And 2 seems to do the trick. Okay, so I will keep it as, I will be dividing this value by 2 because that seems to work. If it stops working, I will just get rid of this whole thing altogether. All right, we have that. Actually, maybe we should make it nice. So I will be, come on, 1, reset, and slowly increase. There we go. And I will be just rebuilding this polyline, rebuild. I'll be just rebuilding this polyline with a point count of, are we using 500 here? So I'll just give it twice as many points. So I'll just be rebuilding it with, nope, that's not how you write 1,000. I'll be rebuilding it with 1,000 points and degree of 3. That's what we end up with. And if I used 500 points, it would be much more rounded, I guess. Maybe we should use 500 points. What if we don't use any points? Yeah, that looks good. Okay, so I'll keep it as it is. That's fine. All right, 2D part done. Now on to 3D. Right, so we wanted this curve to not just grow in 2 dimensions, but we rather wanted to grow in 3 dimensions. So I wanted to create some sort of a form, and I will probably just make it in Rhino. So I'll just create a line segment. It's going to be a fast one, so don't expect this to be a very fancy form. So I'll just create a line segment, copy it 2 times, select all 3, type in rebuild to rebuild it with degree of 3, and yeah, sure, let's see. No, let's give it 4 points and degree of 3. Hit OK. Then I'll type in points on and just mess around with these points to get some sort of a shape. So perhaps this one goes down, and perhaps this one is a bit smaller. Maybe these are wider like that, and maybe this one is also going down like that, and these 2 guys are going up. And should they be? No, these 2 should be wider. I'm just creating sections for a loft. So that's a small one, that's a big one. So maybe this one can be a bit small as well. And this one should be, whoop. Yeah, why not? Something like that. And maybe I'll even kind of move this up, rotate it 45 degrees like that, move this up rotate it 45 degrees like that. I have no idea what I'm doing, but if I loft this, change this to shaded view, you know, I end up with something like this, which is fine. Maybe we can make it a bit nicer. Let me just rotate this other way around, maybe just something like this. Nah, I'll keep this as it is. I'll just have this part, the right hand side, rotated, and maybe I will rebuild this one with 6 points, and I will mess around with those 6 points a bit more. So like that, these two come in, and maybe they bulge out like so. Why not? Okay, loft, delete, flip this guy around. So we end up with a form like this. Why not? I mean, perhaps I should be kind of turning this around like that. Come on, just turn around. There we go. Flip it over. Yeah, let's work with it like that. Okay, so we have this, and then show selected. This curve right here, I think that's fine. We will still be using the same curve. There are a few things that I need to change with the script for this to work, of course. First of all, I need to reference in the surface. So that's a BREP or a surface, SRF. I'll right click it, set one surface, and there we go, it's referenced in. And then I will take this curve and project it onto the surface, right? So that my growth starts on top of the surface. So CRV, or rather we already have this curve here, referenced in here. I will just use project. Project an object onto a plane, no. Project a curve onto a BREP, perfect. Curve is this one, BREP is my surface, direction is going to be Z, you know, I'm just projecting it downwards, so I don't need to change it. And I will not be using the original one, rather I'll be using the projected one, like that. Okay, let us reset the simulation and see how it works now. Turn this back to 0, or to 1, that's important. Run the simulation and start increasing the number. And as you can see, it becomes real weird, real fast. And that's because we just broke 2 dimensions, right? As long as it was in 2 dimensions, it was fine. It worked well. But since we broke it from 2 dimensions, since now it's in 3D, those spheres, they have the ability to push up or down. Spheres, sphere collision has the ability to push up or down. So we end up with this zigzaggy mess. And actually, I should probably be using custom preview on it with some bright color like that. So we end up with this zigzaggy mess, which we, let me hide this, which we don't want, right? We want to fight it. So the way we do that is we use goals mesh, no, goals on, yes, goals on, and we use keep a point on a given mesh. We use this goal right here. Okay, so we want to keep these points right here before the simulation starts, right? We want to keep these points on this surface here, right? So these points come in to the points input, and for Well, there's a problem. We have a surface here and it asks for a mesh here. So we need to convert the surface into a mesh. You can do it in two ways. If you have a single clean surface, then it's easy. You just do mesh surface. Oops. Mesh surface. You just use this tool and you just kind of give it a decent amount, like let's say 50 by 50. That's way too much, I think. Preview mesh edges. Actually, that's fine. Yeah, you just give it like 50 by 50 resolution. And it approximates the mesh, the surface pretty well. That's if you have a single clean surface. If you have like a B-rep, like a messed up collection of surfaces, then you can use mesh B-rep tool. Let me hide this one. You can use mesh B-rep tool and you can see it makes a pretty good attempt at meshing. There's a few weird things here and there, but it does make a good attempt. But I would probably suggest using also the settings quality, either settings quality to get a finer result, or settings custom, and then messing around with all of these settings here. I believe if we just use minimum and maximum edge, or minimum and maximum, let's see, minimum count is 100. And that doesn't really work. 1,000 here. Yeah, okay. So if we use a minimum value of 1,000 for custom mesh settings, then it kind of does a pretty good job meshing it as well. So you can mess around with that. Since here single surface works quite, we have a single surface, mesh UV works well, so I'll just be using that. Okay, let me connect mesh UV to the mesh input, like that, and that's honestly it, right? I will be connecting, let me hide the mesh version and keep the surface version here. I will be taking this point, goal, point on the mesh goal output and connect it as my D3. And now you can see all of these lines are forced to be on this mesh. So let me reset, turn this back to 1, reset again just in case, turn this on, and now just slowly increase the value here. Super. It works. Yay. And as you can see, you know, that the line is not long enough, it doesn't work properly, so I will YOLO it and try and say, what if the maximum result, maximum value is 40? What would happen then? And just kind of keep increasing it. Seems to be doing quite well. And as you can see, at a certain amount, this curve is going to start leaving the boundaries of the surface. That is where collisions, it can't fit anymore, right? So collisions are pushing it out from they're pushing it out from the boundary, from this. So collision detection overtakes the on mesh component here, and they start extending out of the surface. If I keep increasing it, they will go out and out more and more until they kind of mess up, right? So we don't want to do that. Okay. Let me turn off the simulation, hit reset, and now let's see how we can mess around with this. So what if, and let me turn this back to 10, edit maximum 10. There we go, slider to 1. What if for count I would use a number that's 2000? Like that, count 2000. And of course I would need to hit reset, and here yeah, I don't need to do anything here. So now we have 2000 points rather than 500, 4 times more, meaning that this slider right here, and actually let me make it let me color it so that you know it's important. Blob, there we go. Now you definitely know, well, yeah, sure. Now you definitely know that it's an important slider. So now the slider will be will have 4 times more influence because we have 4 times more segments, right? So let's see how those behave. I will start, nope. I will run the simulation and then start increasing my slider. Why are you not? Oh, you are doing something. Yeah, it's growing. It's growing. Just very slowly. So I believe I was wrong. And 10 seems to be very, very, you know, boring. Like, not boring, but definitely not a lot of expansion is happening with 10. That's kind of logical because all of the segments are 4 times smaller. So, you know, they can compact quite more with smaller sphere collisions. But we can fix that. Before I do that, though, I will... for my goal on mesh, I want this to be real strong. So I will give it like 100 strength. Like that. Just connect 100 to the strength. I just want these guys to definitely snap to the mesh. Okay. And now for this one, I will edit. I will type in maximum. And I will say 100. We'll see. We will see if it works. So 100, and I keep increasing it slowly. What if I do it fast? No, it's not happy if I do it fast. Okay. You shouldn't do it fast. That's the name of the game. Okay, let's try again. I want to actually see the polyline here. Okay, that is intersecting itself like crazy. Okay, time to fight it. Reset, run again. What if we say 1 here for this? Remember where we used, where we divided up the radius for the sphere collide? I will get rid of that radius and I will just use, you know, the same number for the line length and the radius. Reset, and let's try. And as you can see, I'm zoomed in. Oops, that was way too fast. I'm thinking. So the problem is that it goes too fast. It can't, yeah. The problem is with this one. It goes too fast and it can't calculate fast enough. So I will be deleting the solver and I will be using let's try Bouncy Solver. I never used it, so let's try it. Okay, so I'll reconnect it, merge to what? Okay, at least we see that it kind of works. And run it and start increasing it and just see if it works. Okay, so it seems to be working, which is good, and doesn't seem to be intersecting. And the reason for that, never mind, there we go, that's an intersection. Okay, so the reason why this is working a little bit better, and let me reset, is because there is damping involved here and also iterations here. Okay, so let's see how we can fix this. First of all, iterations. This many eternal iterations will be performed for each result's output. Okay, so what if we say do like 50 like steps before you kind of showcase an output like that, and then damping 0.99. What if we say 0.95? Would that work? Hit reset, hit run, and increase okay. So this is at 10. Seems to be working quite well. At least I like what I see. Let's increase it even more. 18, 20. Okay. 25. Almost there. Let's try 35. 37. 40. Okay. So we have it working. And it's filling up our whole surface. So we didn't need to go all out until 100. So I'll just hit edit and I'll just say that maximum is like 40. All right, we have it. Nice. We have it working, and I'll just do 40 just to finish it up. All right. Next up, let me turn off the simulation and see how a rebuilt curve looks like. That's pretty clean. I like it. That looks pretty dope. And now the question is, how do we make it, thicker? Because right now it's a curve. Well, we can pipe it, or rather mesh pipe it. Mesh pipe. What the hell are you? I don't wanna. don't care for that. Or we can offset this outwards from the surface. Offset these lines. And there's a trick on how to do that. We have these points here, right? We have these points here, and we're using those points to rebuild the polyline through them, right? And then rebuilding the polyline. And we also have the surface, the original surface. And let me create another surface component. Come on. And drag it. How do we... Come on, I just wanted... Did it... There we go. And let me actually group these two inputs so that they're not lost. And just drag it here. Okay, so we have our points, we have the surface. What if we move those points according to a perpendicular, meaning 90-degree angle vector from along this surface where the points are, right? So I would say, let me hide the move for now. We have these points and we need 90-degree vectors from the surface at these points. So I will go for surface CP, surface closest point, like that. And I will say that's my points, that's my surface, and we get UV P coordinates. And with those, we can go to our surface tab, go to analysis, and choose, there should be like evaluate surface somewhere here. There we go. Evaluate surface. Evaluate local surface properties at UV coordinate, right? UV coordinate is the key thing here. That's why we're using the surface closest point to get this UV point, right? So that we have something to plug in here. Okay, two inputs. UV goes into UV, of course, and for surface, we use the surface from here, like that. Great. So now we have all of the different evaluations, blah, blah, blah. That's all cool. We actually don't really need all of them. We only care about the normal. So I can show you what the normal is if I just type in vector, vector display, and disable this. These guys are normals, right? All of these guys are 90, all of these vectors are 90 degrees. Can I make it nicer? Relative size, there we go. Nope. All of these vectors are 90 degrees from the surface. Super, which means we can move these points away from the surface by using these vectors, along these vectors, right? So I'll just type in amplitude for these normal vectors here, amplitude, to give it certain strength. And I will type in, I didn't work with dimensions with this tutorial, so I have no idea. That is 1. So let's say somewhere between 0 and 10. Like that. And connect that vector to my transform input for moving these points. And I have, oh yeah, amplitude 0. So let's say I will just be moving them by 1 for now. So I'm moving those points away by 1. So now let's find some pair of points where I can explain it better. There we go. This guy right here and the moved version of this one. So this guy right here, right? This one. And a moved version of this one. Right? I will entwine. I will use entwine. And actually, I just need 2 inputs, so I'll just zoom in and click on the minus sign to just have 2 inputs. And I will connect my first points into 0, 0 and my moved points to 0, 1, just like that. The reason why I do this is because, oh, actually, I want to see the surface. The reason why I do this is because now all of the points that I have originally are in one branch of the tree. That's what entwine does. Of the data tree, and all moved points are in the second branch of the data tree. So if I connect it like so here, these 2 sets of points will be calculated separately. So it will make 2 polylines, it will rebuild those 2 polylines separately, right? So I end up with these 2 curves. And it's basically like doing an offset, right? A pretty shitty offset, honestly. Huh. Why is that happening? Hello? Wait. Wait. Why is that going on? That's because polyline is being rebuilt. Can I just do interpolate curve through these points then? Oh, that's much nicer. Okay. Remember when I said that we need to do polyline and rebuild the polyline with degree of 3, blah, blah, blah. Yeah, so we just delete that. And instead, with these two sets of points, we just do interpolate curve. Or you can use NURBS curve. That one also works. Which one? Which one looks nicer? This one looks like that. This one looks like that. This NURBS curve is softer, so I'll go with NURBS curve. That's the only reason. So we end up getting something like this, much cleaner. Okay, we have two curves here. They are in separate branches, but it's quite easy to fix that if we just flatten the output, the curve output here, and just, yeah, now they're in a single list, which means we can loft them together. I'll just use loft and just casually make a loft from them, just like that. So we end up with this beautiful loft here. And I believe we can, now since we have a loft, can we offset? Offset a curve on a surface with a specified distance. I want to test this out. What if we have these two curves here, and we have a surface which is here, going off the rails with this one. Oh no. Oh no, I crashed the freaking script. I didn't save the script. Oh no. Okay, time for a coffee break, I guess, and then we will continue. Okay, I didn't need to do a coffee break. It actually did it in like a minute, but the output was poor and I immediately deleted the output. Sorry about that, but it was poor. So offset surface is not your friend. Instead, what we can do is what we can do is save the freaking file. First of all, desktop tutorial 2020-24, save, and save the Rhino file. Tutorial 2020-24, save. All right, and now we can try and offset surface. Why not? There's another one that pufferfish component has, which is also called offset surface. And I just want to use both of them just to see which one is faster. Right, so this one is pufferfish, this one is the original one. Let's start with the original one. That was way too fast. Something's off. Oh, that's because offset distance is 0? What the heck? Let's do offset distance of 0.1. There we go. That's the crash that I was waiting for. Come on, you can do it. Okay, that wasn't that bad. Where's my Grasshopper? Hello? There it is, 10 seconds. Okay, and with 10 seconds we end up with come on, just give me, there we go. Two surfaces here, and then let me make it high quality. That didn't change anything, but then we can loft between them easily and just kind of create a closed ribbon. What about offset surface from, I should have checked what the distance is. We'll see. Let's see offset surface from the pufferfish, if that is better or worse. And it seems to be much more worse. Okay. Time to pause the video and continue once it's alive again. Alright, so that one took 1.5 minutes to do. So let me just delete it. Instead, we will be using offset here, and I'll be showing you how to make it much faster as well. But for now, offset seems to be the way to go. Alright, so we have two surfaces here. The offsetted surface and the original one. And we can kind of connect them together by just doing by just lofting between the top edges of both of these surfaces and the bottom edges. And to do that, I will just say give me edges, rep edge of, let's start off with the offset surface. Of course, it's gonna give me 4 exterior edges. 2 of them are going to be planar curves and 2 of them are not. And I will just say measure the length of these edges, right? So I have 4 lengths. 2 of them are very big and 2 of them are small. And I will say sort list, so sort these edges from smallest to highest value, or sort these lengths, and together with them sort the edges that those lengths correspond to. So I'm sorting the lengths and I'm taking the edges that those lengths belong to and sorting them together. So now all of my smallest values are in the shortest edges are in the top, and these 2 really long ones are in the bottom of the list. Meaning that if I right click on the A output and click on reverse, then the ones that are longest are in the top of the list and the ones that are shortest are in the bottom. I can do list length, list item, connect it, zoom into it, and click this plus sign here. So now I have the first edge, which is the one that's closer to, the one that is further away from the surface, meaning this edge right here. And I have +1, which is this edge right here. How do I know that? That's because this edge right here, since it's further away from the surface, is going to be longer because it needs to travel further. So that means it will be at the top of the list, and this is going to be the second one. So I will be grouping this and copying this whole shebang with edges, length, sorting, and so on, and using it on the original loft as well, like that. Okay, so I have these guys. Then I can loft between them. So I will take I from here and holding down the shift key, I from here, and just loft those two together like so. And I will loft again, +1 and +1. Okay. Easy. So now we have this surface right here, this one right here, the top and the bottom. I can merge all four sides into one single list, like, come in here, like that. So the loft, the offset, and two lofts here. I merge them. Now they're all in this single list here. And I will just flatten it to just make sure that everything is definitely in one list. And I will use, what will I use? I will use brep join. I will join them up into a single brep component. And for some reason, this guy starts crashing, but then it stops, which we're happy about. Okay. So this one is a single brep, which is open, but we can close it by just using cap. Cap holes, close it off, easy. All right. So that's how you do it. This whole part here is how you do it when you want it to be a single closed brep. If you want it to be a single closed mesh, and let me make it pretty for you. Said make it pretty, there we go. If you want it to be a single closed mesh, that's easier because this loft is an interim surface, meaning that we can use mesh surface here on this loft like that, and we can just specify number of quads in U direction. I believe that is 1 because we don't need any quads in this direction, but we do need a lot of quads along the other direction. So this one is going to be, let's try 1,000. Yeah, so 1,000 is definitely not enough. 10,000. 10,000 seems to be okay. That's good enough resolution. And then I just use either Viewerbirds transform mesh thicken, either this one or pufferfish offset mesh, which one you want, whichever one you want. Let's see which one is faster. Viewerbird is a little bit faster, so I will be sticking with Viewerbird. Distance is set to be 5, which is way too much. I believe we used 0.1, yes. So 0.1 for distance, and there we go. That's it. So that's with a mesh, it's much faster, but it's a mesh, so that there's a trade-off there. I will be probably, how do we do this? SRF surface like that. Oh no. Okay, now we wait 10 seconds. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Oh, less than 10. Actually, let me just select all of these and disable them so that they don't calculate, because I don't really care right now for them to calculate. And I'm just cleaning everything up so that everything connects from here. Just like that, and then I will create a data dam like this. There we go. And let me just scribble heavy stuff. If you really need it to be a poly surface, then use it. You use this. There we go. Oh, by the way, the files, of course, are going to be in video description as per usual. So you can just, the lazy bastards can download them. All right. So we have our mesh done here, and then we have our surface here. That's all neat. I guess it's time to bake it out and create a nice render, because we're kind of done with this whole thing. Maybe the last thing that I would probably do is, well, this one is quite, yeah, I would probably create another data dam just here, so that when, just like color, no, that's a bad color, there we go. Just because when the solver is running, we don't want it to keep recalculating, you know, over and over the mesh thicken. Other than that, that's whatever. Okay, where was I? We're done with this tutorial. Hope you've learned something new, and now you can grow stuff on your beautiful facades or bike saddles. Yeah, let's go for a bike saddle here. So you can grow stuff, you can 0.2 maybe. You can thicken these bad boys up a bit, and so on. Make them nice. I hope you enjoyed it. I will see you guys on the next video, which is gonna be on Wednesday. Bye.